It's already there, right?
Yeah, you just have to press the X button when they're not hearing anything.
It's already recording.
Yeah.
Okay. All right. All right. Thank you, everyone, for all the questions during the break. I enjoyed the discussion. So, as I said, the principle is the same with multiple sources of time series. Let's say in urban setting, you can add a graph representation as well. And in this kind of thing, for example, in what is the different? Let's shift that. Okay. Some of the new things that we introduced here, for example, is the multiple graph attention block, right? So if you're adopting transform architecture, you either introduce or bring your own embedding for each of your series, or come up with your own loss function, or build your new attention mechanism. In this one, the Ichkai paper, the contribution is the new attention mechanism that learn across the different attention block of the different features of this graph, for example. Okay. Now, the question again, going back to SSL paradigm, less is more. What about if we have limited training data? So an example for doing training or doing pre-training for spatial temporal data with SSL paradigm is applicable for things like forecasting on new roads.
It will recover.
Okay. Forecasting on new roads. For example, can you pre-train on one part of a road network and then either zero shot or fine-tuning on new road network that you've never seen before? But how do you do contrastive learning on this paradigm? For spatial temporal data, what we introduce here is a new spatial temporal split. So this is the splitting strategy is basically looking at how would you split your training data into this training, validation, and testing in such a way that we have this here. The idea is can you actually split the data into 9 subsets, and each of these subset combination will then help you to know which split of the data is used in training, which split of the data is in validation, which split of the data is used in testing, in such a way that there will be no overfitting, but also your pre-trained model could be quite robust to the different variations across location and time. So this is basically the contribution of the paper. This is a very naive visual of how it is done. Okay, what it makes sure here with the bottom row here is there's a new setup where not all roads will be seen during training. Okay, so then we can do forecasting on those new roads. In fact, there's a lot happening like this in Australia. We have a lot of new roads being built all the time, and people need to forecast what that looks like. And typical traffic engineering is they just build some sort of like graffiti model, agent-based simulation. But what if we can just use data to do this? And then we apply our proposed spatial contrastive pre-training. Okay, so this is actually very much similar to contrastive, the sim clear paradigm, but then we use the data set that has been done on the spatial temporal split here. Now, let me just skip. Look at the data set. The popular data set for traffic flow forecasting that has been used in many papers in KDD, in NeurIPS and all that, are very much a subset of the real data. So the original PAMS data has 11,000 nodes and more than and nearly 240,000 ages. A lot of the papers are using the research subset, which is this one. Okay, you see, when you see PAMS Bay, that means it's only 325 nodes rather than the 11,000, and only 2,600 ages. These are the most popular ones. Only one paper that used the original PAMS Bay before our paper. Sorry, before, not PAMS Bay, original PAMS dataset. And to be honest, training on this took a long time because of the scale of the number of nodes. But also, this paper used a lot of feature engineering for each of the node because the behavior of each of the sensor is quite different, as I showed you before. Now, what about if we take it to the extreme? We apply our SCPT, the spatial temporal splitting strategy, and we only use 1% data in training, and do validation testing the rest of 99%. So that's what we did. So what you're seeing here, this is the original graph WaveNet. Okay, you can see the cursor. And this is the one that takes that does the full training on the whole network. Training time took 7 days. I think this was using 4A100. Okay. The training time took 7 days for GP, just DCRN, and this is state of the art. Now, what about if we just use the backbone of graph WaveNet and test it only on 1%? Our training time just took only 22 minutes. And what does the error looks like? MAE is 2.0. Ours actually improved the original graph WaveNet with SCPT split. Okay, error is lower, better. Okay. And there is still a big difference to GPDCRNN. But what you can see here is we only use 1%. We didn't do ablation study. Maybe if we increase it to 10% seen in training, it will have beaten the GPDCRNN. But what I'm saying here is the paradigm is the same. If you know how to do SSL wisely, you don't need a fully supervised method. Pre-train, you don't need to pre-train all your data. Okay, you need to know how to select. So data quality is important. Embedding, knowing how to do augmentation properly is important. And what is interesting here, our model using SSL paradigm even works well on long forecasting horizon. All right. Now, big data set on time series. I'm gonna get there. There are some data sets that I'd like you to take a look. For example, this one. We have collected what we call XXL traffic. Let me just remove that. Extremely long traffic data set. So we crawl PAMS website and also in traffic for New South Wales. website. Extremely long because it covers more than 20 years of data. And this is good for study on like looking at distribution changes on the census, right? You could see, for example, this node here, the density of the traffic in 2005 and 2024 look quite different, huh? It's the same sensor. Some actually could be quite similar, but some are quite different. All right, and even some of the changes are quite feasible before, during, after COVID. Some patterns are completely different for each of the sensors. So if you want to do study on long-term forecasting, this is a good data set for you to look at. And we also have aspect where new problem that we introduced, testing with gap. What I mean, testing with gap, potentially the road is closed for construction, you don't have data. You could be, some sensors could be faulty. Yeah, we introduced new benchmarking. And if you want to know all the state-of-the-art methods, we've collected them in our benchmark. This one include Member, iTrust, dLinear, Autoformer, Informer, FedFormer, Patch TST, SDGCN, Graph WaveNet, and our own one as well. Everything's there. You can just fork them, implement them as you like. Okay. And we also measure training time per epoch. So if you want to pick and choose, for example, which model to choose, there's a trade-off between speed and accuracy. We have them as well in our benchmark. So again, paper link available, and also the code is available, and the data sets available. And in fact, the thing is, not only prediction we're interested in optimizing our prediction, because there's a different varying level of difficulty in time series and spatial temporal forecasting. So this was a paper from 6 Spatial last year. So it's a bit like math. There are some easier math equations and harder math equations. Same thing in time series spatial temporal forecasting. There are distribution that's easier to predict. There are distribution that's harder to predict. So how do we then combine the best things out there? But we want to learn to optimize as well. So we then come up with a new formulation, which is spatial temporal quantile forecasting, because we want to learn also the distribution. So we're not only interested in predicting exactly the point here, point by point, but we want to predict this range here, the quantile. All right. So, and the output of this paper are both the point as well as the quantile. So we introduced curriculum learning for forecasting in this 6 Spatial paper. So, and the way to do this then, we can then start to visualize the nodes that are easier to predict and the nodes that are harder to predict based on the distribution. And there are 2 categories as well. There's easy sample spatially or easy sample temporally. So there's in terms of the quantile metrics. I'm gonna skip the details, take a look at the paper. So we just extended formulation of curriculum learning for spatial temporal quantile forecasting. All right. And we basically have a scheduler for the curriculum learning to learn the curriculum of the quantile for the temporal distribution, spatial distribution, and across. Okay. And then we have different strategies. Should we start from easy to hard or from hard to easy? Which one is better? All these are in the paper. I can't remember what was the inside. Sorry about that. Anyway, again, this paper gave you a lot of different implementation of the popular graph transformers out there. But we added also our own curriculum learning scheduler for you to adapt. And the takeaway here is adding curriculum learning scheduler help you to optimize your forecast, both on quantile as well as point. And it's also giving you a range of the likelihood of error, which is nice. In fact, we learned about, we had an idea about this because people who we work with, the transport department, traffic departments, they're not necessarily interested in the point or the error, but they want to know how confident are you in your forecast. So they're interested more in the quantile. Okay. And what is also interesting, using curriculum learning, the forecast performance converge much faster. So you will take less of your GPU time if you use our scheduler. Okay. Another aspect of using, so curriculum learning is one of the paradigm from RL. Another aspect of using RL is, for example, how much data is enough for forecasting? Do you need to collect all your data before you can start? How much you need? And we then adapt. What we introduced here, this is a KDD paper last year. We introduced a multi-objective RL to adapt the goal for when to start learning. Do we need to start predicting now, or do we have less data? That means accuracy will be lower, but there's a trade-off. We can actually detect. We can be more timely in our prediction. So in this work, for example, we generate the state information from the prediction. Okay, we have the spatial temporal prediction to predict the states, but then we generate the state information to determine the optimal prediction time for each of the nodes. So we make it dynamic for each of the nodes when we can start predicting. Okay.
So, Flora, have you looked at the prediction in the past? So we have this one paper called data postdiction, which aims to predict the past because you've trashed it already for saving storage, basically. So could these ideas also be applied in this way?
Yeah, I think what you're saying maybe is more like experience replay. That's more like continual learning. Mm-hmm. I have not included some of our work in that part. There is a work that we did where the problem with what you're saying, is it because you're not predicting the past because
you don't have it anymore. Yeah.
Right. You might have new pattern that's emerging that has not that the model has somehow forgotten. There's the biggest issue with anything deep learning, which is catastrophic forgetting, right? And there's a more bias to recent data. So we can actually have a buffer in memory. And the most popular method is called FSNet from Salesforce, to have a memory buffer to store unique events. In fact, I do have work in relation to that, but I don't have example on the big one. Let me just scroll.
Is there anything similar to RAG?
Yes, of course. I'll mention RAG later. That's when we do our work on LM. I haven't included anything about our RAG work, but I'll mention it later. So in here, for example, on extreme events, we have a project with energy distribution company where I'm not sure about here, but electricity prices in Australia is very dynamic. It's based on generation in the market, because everyone now has their own solar rooftop and battery and all that. They can also sell back to the market. And also distribution company always want to know being able to forecast accurately on energy. But the problem is during lockdown, for example, of course, energy load goes down in office buildings. This was in my office building CBD. But then to predict how much is the demand for energy when people recover from lockdown. So these are 2 lockdown periods, for example, in Melbourne. Predicting this part is a bit harder. So how do you then remember, especially now you have repeated lockdown, not only you're learning first time, I've never seen this before. And then we relearn. So we have a paper where we try to learn the out of distribution for energy forecasting, but we just adapted FSNet. FSNet is a method from Salesforce that has the look back window here. Okay, so it's not only looking forward but also look back. And what is important is they have a buffer. I don't have it here. I don't have it in this image, but what they have in FSNet, they have a backbone that actually has a memory to store the distribution changes over time. And this buffer is actually quite expensive to do. So our work here was the first that actually completely buffer free for continual learning. So you can do continual learning buffer free. And what it does here, we actually have a latent VAE model that we're storing. And this latent VAE is based on being able to store the continuous ODE representation of each of the sensor. And why ODE? To be honest, these days I like working more on ODE representation more. And then if needed, you can add the things you like from transformers, like for example, the key value mechanism from the attentions, then you can actually use it, but not in this one, in another work I'll show you. So in here, we actually have a latent ODE for that sequence, okay? And if there's a new streaming signal coming in, we can do dynamic online fine-tuning. How do we do that? We can update the parameter of this model by seeing if we can reconstruct the latent distribution over time. So this is the robust model, and in this part here, we tackle the concept drift by learning the dynamic of the distribution rather than memorizing the past data point. So we memorize the distribution. Okay. So so we generate a prediction in the future and also in the past. We do this dynamically and we update the parameter over time. So this is this can be done per signal. You can also do it multivariate if you like. Basically, this is an ODE VAE model. All right. What is interesting here, our work is much closer to ground truth, but also look at the computational resource needed. FSNet, because of the need for buffer and storing the data points, execution time takes longer. Ours is much faster. So again, the code is available on this one. I will now quickly go through I want to quickly go through irregularity. Okay. So we've covered a lot of things except irregularity before I want to talk about LLM or time series. What is irregular time series? Okay, hands up if somebody can tell the difference between left and right. Yes? Yes?
For the left one, have the same timestamp, but not for the right.
There you go. I have a present for you. Come and grab your Vegemite. Have you tried this?
What's that?
This is Vegemite. So you have this.
Thank you.
So spread it on your toes, okay? But they are not like, do not do it like Nutella. Do it on batter and spread thinly. It's like soy sauce. It's very healthy. It's a lot of vitamin B. I hope you like it. Spot on. You have good eyes. All the two channel of time series are regular. You know, let's say the timestamp is every 15 minutes. Look at the second one. One is regular, one is irregular. Okay. Now, what you have to do this typically, if you have this kind of time series, if you use something like transformers, ideally you need to impute them before you pass them to something like transformers because it has to be discretized, right? And this is the problem with transformers, which is why I have a love-hate relationship with transformers. It's nice because it's been designed nicely. The idea of using position encoding, embedding, and then you have the attention mechanism. But the thing is, it's quite heavy. It's you also have to discretize everything. That means you lose the continuous representation of that time series. There should be better things out there than transformers, and we've been investigating things like what I call ODE-based and PDE-based neural network. Because in fact, what you have here, you have observation between data. If you actually make an assumption, I need to impute my data. Maybe this is the time series observation. Maybe let's just do an averaging between the two, shall we? So you cannot just do simple averaging. If let's say your actual observation is a bit like this, right? So what we believe here, there's a hidden trajectory of the time series. And how can you actually learn this in the latent space without having to impute this missing data because all your sensors do not line up. They don't have the same timestamp. So the way we do this is we believe we can adopt the idea of ODE where we can actually, ODE stands for ordinary differential equations. It actually models the flow of data between the two observations. But what we also believe is we need to know the relationship between the different variable of time series. So across the series, we can have the learnable ODE if there's some information that's missing, we can borrow information from other channels per se, okay? And how do we do this? The idea is pretty simple. Let me try to zoom. Where's my, there you go. Okay, you start with an input. You start with an input here of time series, and you can have information that's missing, for example. Can we build a denoising autoencoder, ODE base? And how do we do this? We actually have, whenever we have original data, we just do corruption. We corrupt the data. And then we have an encoder-decoder network, which is based on ODRNN. ODRNN, look it up, is a very famous NeurIPS 2017 paper, best paper in NeurIPS. That's one of my favorite papers in NeurIPS. So you then come up with a data that's reconstructed with minimal error when you compare with original data. Okay. So once you have that, you actually have a latent representation that knows about this data very well, regardless of how corrupted. I mean, how if they're missing or whatever. Now, remember this data already has some missing information. This one was further corrupted, but then reconstructed. But we already have ODE latent representation for each of the input series. Now, can we build? Now, how do we know if, let's say you have 5 different sensors, and you have the latent ODE representation for each. How do you know that this latent ODE sensor A is highly correlated to sensor B or C at this time? And that's where we build this pyramidal attention mechanism that map the sample latent representation, okay, and we sort them. So we learn the representation and sort them based on the importance. Okay. So we find the attention score between the sample here and the learn latent representation, because it's also learned to predict. And if they're actually highly correlated, with the loss is quite minimal, then we know these are highly similar, and therefore they are pushed towards the top of the attention mechanism. So we'll end up with a link ODE representation here, where we can link the two ODE latent representation. We can link the hidden state learned by the ODE of other samples. All right. And can we do this on different tasks for time series classification as well for forecasting? Can we do it for different data sets? You can see the data sets quite different. One is electricity, one is transformer, weather data. We even have mimic. Mimics are health time series from hospital in ICU. So what we did was we just randomly corrupt data set and see if how the sequential link can reconstruct them. All right. So for example, here with the baselines ODRNN, we could see how close or far we are to the reconstruction, to the ground truth, sorry. So again, the code is available. Take a look. What you can do here, then you can use this as a plugin for your highly dimensional time series, if you like, to generate imputation. See if it works, and yeah, I'm keen to hear more. So this could be used for imputation. It could also be used for prediction. All right, I've covered quite a bit. Now I want to talk about datasets. There's a lot of datasets, time series datasets out there, but they're actually very small and naive. Some of them are quite even synthetically made. Okay, but we have released, I would say, the biggest time series dataset last year in NERPS called Buildings Time Series. Apart from XSL traffic, this is a NERPS dataset, Buildings Time Series. You like this potentially if you also work on knowledge graph. So it has more than 20 classes. It has more than 15,000 sensors, more than 3 years. Where do they come from? Look at the image on the left. It comes from 3 different buildings in Australia, and they could have different smart sensors, from energy, from EV charging to voltage, to water sensor, temperature sensor. And And we also have information about the association of a class to the brick schema. So in buildings, people are interested, the ontology is used is called brick. Okay. There's a lot of data sets out there. I'll just skip this, but it just says that ours is the biggest and the most comprehensive and the longest and so on. So what does a data set look like? So for example, let's say you have a time series like this. This is a brick schema. Okay, so it doesn't have just to tell you that this is an air temperature sensor, because a sensor that looks like that could be water sensor. The problem is even an air temperature sensor could look different, whether it's inside a chill bin, is it inside aircon, or is it actually an outdoor temperature sensor? So the problem here is the multi-label classification. It's not just knowing what it is, but where is it? Okay. And you can use this if you want to do building analysis. If you can use it if you want to do time series classification problem, time series forecasting problem, time series imputation, whatever you like. If you are combining time series and knowledge graph, this is a great data set that has them. It is actually quite real world. So what you see is what you get, because some of them are showing real world anomaly. And we have two benchmarks. We have the multi-label time series classification, and we also have the zero-shot forecasting. So in the multi-label classification, we have the benchmark for the basic one, like the boosting, the bagging and boosting that you like, random forest, to the variant of the former, and also delinear and patch TST. Okay, these are the newer models. These ones are typically better, like the delinear and patch TST for classification these days. We also have a benchmark for the zero-shot forecasting. So that means train on one building and test on other buildings.
What is the forecasting task?
This is forecasting task, yes. And this is the classification task, which means
what was the forecasting task for the building scenario?
Forecasting the time series sensor. So it depends on the sensor. If it's a water sensor, can you forecast what the water sensor value will be? Every single sensor, just predict the next horizon up to, let's say, 7 days, 1 day, whatever it is. That depends on, because each of the sensors have different granularity as well. We actually released a machine learning competition on this. We had in the web conference earlier this year. What was interesting, this was not using any feature, right? These are all using raw data. Competition was only 6 weeks. We released on AI Crowd. All the top 3 competition winners, they all use XGBoost. Accuracy was, F1 score was increased up to 0.59 or something, but they use hundreds of features for each of the sensor. And when I get some of my undergrad students to rerun their code, some of them took so long to run. So I think there's still a lot of space to improve. How to improve these kind of models, right? To get better F1 score. But again, this was done completely raw. We didn't do any nice things. And we didn't do a new way of embedding. We didn't do SSL. There's so much things to be done on this data set. Yes?
In this multi-level classification task, what are the number of levels, like the total number of different classes?
Yeah. So here's a good example. So you have this classifier. You have the time series, and you need to classify whether this is a sensor or not, for example. Okay. And whether it's temperature, if it's temperature, is it air temperature sensor, is it outside or inside? So they're about what?
So
about 10.
One is classifying is positively. The negative one is
Yeah, so this is more like binary yes or no.
But there is one intermediate step that is zero, I can see.
So this is not applicable. For this one, these are not applicable. -1 means it's not applicable.
Not applicable.
Yeah.
And zero means here?
Yes or no. Whether that label is applicable or not. So this label is taken from the knowledge graph. Okay. All right. We have a lot of other sensor data. This one was released in Nature Scientific Data. We have data of high school students wearing smartwatches. Sorry, we not smartwatch, just wrist-worn wearables. And we have indoor and outdoor weather station. And we even know where people sit in classroom across 4 weeks and what classes they took, whether they took math or politics or language. And we get them to, after every session, like for example this, before and after, we ask them to measure, do self-report of their cognitive, emotion, and all those things, and we measure them. So we found interesting things. For example, cognitive level was so bad in the afternoon when CO2 level is high and it's hot. So, and especially when it actually affected performance on their math classes. So because of these, then the school could use this information to change the heating and cooling strategy, or even the scheduling of when should they put math that requires more cognitive engagement. Maybe put them in the morning rather than the afternoon, or things like that.
So they were reporting their cognitive function?
Yeah, they're reporting it. We use a gold standard survey, education survey that actually has a cognitive.
But not everyone is self-aware, right? I mean, this kind of survey, I mean, it depends on people.
I completely agree with you. I completely agree with you. That's why we have to baseline it. That's why with the arousal and the balance of this coming from the senses. Okay.
Have you also special information about the students?
Yeah. Location where they are. We couldn't collect GPS data. It's not because they are underage, like they're 15 years old. But we have location in classroom where they are, where they sit. Yeah, and we know over time, sometimes we know whether this student always sit with this other student, whether they're when someone is the arousal is higher, the other one also basically wants someone to get excited with lessons, whether they actually influence the others or not. Information like this was quite interesting. We have papers on that as well. Another data that we released recently, this was more just about 1 month old, is massive steps. Okay. We have a lot of check-ins data. Typically, you only use, how many of you have worked with check-in data? Not many. You use Foursquare maybe, right? Goala. Or there's I think I know you've been working in human mobility, right? The Japan one, Yahoo Japan one. But not many. So I think this is the biggest semantic trajectory data release. So we have cities even from Istanbul, Kuwait, Sao Paulo, and places like from Jakarta. So within a month of release, we have 2,600 downloads already. So feel free to take a look. Including the benchmark was released. Now, I want to move on quickly to, I have 45 minutes. LLM. Or time series forecasting and classification. So can we actually now use something like ChatGPT or Gemini to do forecasting or classification? That is very much the question. And this is quite an important thing because I have in the past, for example, developed some sort of tool for city councils. This is the tool I developed for Melbourne City Council, not the left one. The left one is done by my colleague. It's a visualization of people movement and check-in at different locations. It's not really check-in, it's like sensors. And the question is, can we forecast how many people will be in each of the location the next 14 days? Because they need to use it to plan, for example, if there's gonna be a football game in a stadium, how many people will be there? How many people will be in that cafe? Do we need more staff? All this information is used for transportation planning and all that. So for example, the tool that we generated, create a daily report for every sensor for the city council to use. This is basically the hourly trend that will happen the next 14 days. And it generates this refresh daily report. But for this, we use the techniques, this was like 10 years ago. We use regression-based methods plus back then it was still just LSTM and improve the method. But somebody came to me recently saying, can you do this using language models? Do we just input historical data? I like to get this kind of report.
What is the input data for this?
Historical flow.
From what kind of sensors? Because I mean,
people counting.
telco big data.
People counting like camera, infrared sensors. It count how many people in and out the flow.
At certain locations.
Yeah, these are like, yeah, multiple sensors in the city. And the data is publicly available anyway. Anyway. So we actually have started, maybe I'll just. So this is our roadmap of forecasting with natural language. Our first work on framing forecasting as natural language was done in Wisdom before ChatGPT was released. Wisdom was February 2022. And let me just go through, take you an example. So I already show you how you do forecasting with transformer-based architecture. You do encoding of your historical data, right? And you embed information one by one, information that you need to bring, and then numbers in and numbers out. But what about if you can, instead of forecasting numbers out, can you describe, can you transform this as sentences, and where the language model could understand this sentence, the semantic information will be in the sentence, and it has numerical patterns, and you ask a question, so how many people will be here tomorrow? Will they be able to give you an answer in natural language as well? So that was really purely just an exploration for us. We didn't know it would work. Okay.
But from the side, when the historical data is quite large, there are not max tokens.
Very good. I'll get to that question later. So we move away from this typical feature transformation paradigm, okay? Rather than getting the data transformed into embedding and then encoder. But what about if we move it to a language paradigm? So everything is put it into prompt, pass it into LLM, and then we can get a response. The first work was this one in Wisdom. We designed two branches, encoder, decoder architecture. One is a natural language branch, and the second one is a numerical branch. We call it mobility branch because we use mobility data, check-in data. The reason why was we were not confident the natural language branch itself is enough. We believe we still need to introduce the branch of numerical to be able to predict the numerical value, and then we can reduce the loss between the two by introducing this prediction loss. Okay, so how did we do it? Back then it was pretty simple. Let's say again, I need my zoom tool. Your input is a POI semantic, observation time, mobility data, okay? And then you describe it. POI 88.1 is optical goods store, and observation time from which day to which day, and how many people, and target, okay? And the result is, this is the template I want you to generate this way, okay? We use safe graph data coming from 3 cities, NYC, Dallas, and Miami. Those are the statistics. Now, surprise, surprise. We have a comparison, our model with the numerical time series forecasting from linear regression to transformer-informer based method, and sequence to sequence, just BART and all that. Ours that have the 2 branches, actually either the first performer or second performer across. And we were quite surprised with that. And we look at alignment between the 2 branches and looking at the attention mechanism. It looks like the model is capable of associating certain numerical patterns with certain semantic category. So it's actually learning that way. Okay. So once we have that intuition, then we know, okay, potentially it's already happening in a pre-trained model. So back then there was already some pre-trained model like GPT-2. There's not even GPT-3. So can we actually use pre-trained language model right away for forecasting? So this was a 6 spatial paper in, again, same year, 2022. So once we work on wisdom, we know there's something there we could use, potentially existing decoder, like let's say GPT-2. Okay. So the decoder here is GPT-2. But the thing that is new here is we know that the numerical pattern is aligned to the category. So we introduce a new POI category classification, and we add that as a token here. Okay. And then there's a and then we pre-train the language encoder, and I'll show you the language encoder that we use later. Okay. And we have 3 different prompts: the basic, and then the second one is remove POI ID. Okay, so rather than using 385, we just say the category. And finally, we use this version where we have to explicitly mention the category or the target, POI category target. Okay. And what you see here, each of the POI has different pattern across Monday to across the whole week. So we found that adding this PO category target explicitly help the learning. Now, what you see here is, so we have 3 small LM encoder: BERT, Roberta, and XLNet. That's the encoder. Remember, the decoder was GPT-2. It was quite surprising. This is RMSE, right? Our models, the best one is actually BERT-based encoder with auxiliary target information. It's beaten everything else.
But how to know that this would be good
Well, RMSE, as you know, is always the lowest.
But always, but there should be a threshold, you say, this is good, this is bad.
I think it's very dependent. I have no idea because it depends on each of the business, right? Whether they think this is good enough or not. I have no idea, right? But we just follow the metrics, RMSE in the paper. And we did a couple of different experiments as well on, what is it? Zero shot. So train on, for example, NYC, test on Miami and Dallas. The model outperformed all the other ones, surprisingly. And because of that, we released Promcast. This is something I'd like you to all try. Because Promcast is a dataset and benchmark, cover three domain, mobility, weather, and electricity. Hundreds of thousands of data instances there. We given you the data that's already in prompt format, especially for the safe graph one. So, and we also include 20 methods. They are based on numerical paradigm as well as the language model paradigm. This was a bit old because it was submitted in 2022, published in TKD 2023. So some of the models will be a bit newer. There are a lot more newer ones. So now the safe graph one is quite valuable because now these days you cannot obtain this data anymore. You have to pay a lot. And even if you pay, they will not give you the daily row count. These days they will give you only weekly. We got a daily row count every hour on these POIs. And they allow us to publish this data because we publish them as a prompt rather than the row. So nice. So yeah, data from temperature of 100 cities, electricity consumption of 50 users, or safe graph check-in of 324 POIs. And what does the template looks like? Let me just show you an example here, okay? Let's say air quality, right? And from May, so A and B, the prompt is that long. Now, we come up with a better prompt. Again, the way to prompt is important. So, and then the output here, and we can use this to pre-train the model, okay? And the benchmarking of a 15 time step predict the next time step. And we also have the multi-horizon one as well in the paper. Again, we have comparison basic numerical. And now we have not just 3, we have 10 language models. From T5 to Pegasus, Big Bird, Electra, Roberta, all of those ones. And even if some data are missing, we found language models are quite robust, being able to do that. So we also have different settings. Observation 7 days, predict 1 day. Observation 15 days, predict 7 days, for example. We have all this comparison in the benchmark. Again, there's always no free lunch, of course, but the free lunch for you, the implementation was already done there, or you can just fork them. Zero shot setting works very well too. Now, this is an interesting figure I'd like to show you. By the time we did major revision submission of the TKDE paper, GPT 3.5 was available. So one of the reviewers say, could you please do comparison with GPT 3.5? I say, okay, why not? That was the best model back then. What you see here, the x-axis is RMSE. The y-axis is costs in US dollars. So where do you want your model to be? Left and down. Another Vegemite for you. There you go. Okay, you want your model to be sitting here, right? Low cost, low error. See where ChatGPT is? The black square is there. That's the cost for calling the API, the token cost. And what is the cost that we have here? Is the cost we host them on AWS instance. There's the cost, basically. If you host them locally, no cost for you. But to make a fair comparison, we just say, okay, we'll serve the model on the cloud as well. And the cost is to serve that. And the error prompt cost is the lowest in comparison as well. And this is prompt cost with BART. So the takeaway here is, if you know how to fine tune your model, you don't need big models. Small language models will do. But you need to know how to fine tune, you need to know how to prompt.
For the cost, if it's the real cost or an estimated cost for the API code. Because when you have large data and you use ChatGPT API and so on, it will be very costly, right? So usually
It was just the cost basically on exactly what the test data.
So it's a real cost.
Yeah. Yeah. So this is all the inference cost, what you're saying here. That leads me to another paper, 6 spatial paper, which is how do you improve your prompt? Because that's a problem, right? How many of you every day trying to communicate with ChatGPT or Gemini and keep changing your prompt to get what you want? But how do you do it automatically for spatial temporal data? This is where we come up with prompt mining.
But was ChatGPT 3.5, was it trained on spatial data? I mean,
We can't, because it's completely,
it wasn't, right?
it's zero shot.
In 4, I remember they started to understand, maybe they trained on OpenStreetMaps because it started to understand, spatial landmarks, notion of distance, these kind of things. So
But
which tells me that they probably trained on OpenStreetMap. And OpenStreetMap also said at some point that they would be issuing
yeah, I think
foundation
the
model.
performance gap will be getting closer. I think you're right. It was,
the
but I haven't done.
3.5 had no clue of either the temporal dimension or the spatial dimension. Yeah. That's true, right?
Yeah.
So if you ask a spatial query nowadays on ChatGPT, it understands spatial semantics, but to a certain degree, not like.
To be honest with you, if the work has been used and inspired others. Some others have now built a fine-tuned llama, for example. Maybe they compare GPT-4. I haven't seen some of the new results, but I think there are some replication of that using newer models. Maybe people in this room can try it. The code is publicly available, data is publicly available, and you can try it yourself if you have it. All right, but in here, what I want to show you here is not all the prompt is the same. So can we actually do this prompt mining and refine the prompt automatically for spatial temporal data for forecasting tasks? That's the whole framework. So we have a pool of prompts. Okay, and the key contribution here is the prompt quality evaluator. The prompt quality evaluator evaluates the entropy across different prompts and looking at entropy of the numerical data being presented as well. So it's a bit like adapting our IGTS idea for segmentation, but for prompt. So we're trying to increase the diversity of because sometimes some prompt, you change it a little bit, it doesn't make much difference. So we want to increase the information gain.
Did you try DSPY? Do you know the framework DSPY?
No.
It's a library offered by Stanford, which does the same thing.
Okay.
So it's like black box prompt.
Yeah, I wasn't aware of it. This was the work. This work was done also quite early, from 2 years ago, published last year. So maybe that's quite new. From the library, maybe.
I think it's like
Yeah. So this was already published in 2024. And this was done very much to compute the entropy of both the text as well as the numerical data, and trying to basically improve the quality of that prompt. And we have a way to measure the quality of the prompt. Okay. I'll skip that detail. You can do that. Sorry. Skip that. Yeah, look, you can do that actually for energy data as well. So, for example, with energy data, you have time and usage. You can add context. For example, it's raining. You can add on whatever context you like. And you can do that autoregressively as well. Let me just skip this.
Can you show that again for the? Oh, so what exactly is the time series they're including? Like just EV charging, because you went through.
It could be building. It's building data. So let me just show you. Energy use of this building, for example. Every fifth.
So it's energy meter data, and you try to extract from that activity recognition?
No, just to forecast.
Just to forecast.
Forecast the future timestamp. What is the energy use?
But I also wanted to ask this earlier. Have you looked at the problem of extracting activities out of this? Let's say when the car was charged, or when
disaggregation. That's disaggregation problem. Yeah, no, I haven't done that one, but there's a lot of work.
Yeah.
Okay. Now I want to talk about trajectory, because this gets into the interesting question about your data is longer than your window. Okay. So the whole idea here is, let's say you have this for POI check-in or for mobility prediction, you want to predict where the next POI where the user will be. Now you can parse the check-in records for the user. Now you imagine some users are very diligent in checking in, so the history will be a lot longer. And this time we use Llama 2. The Llama 3 was not released. So the context window was small, unlike the new version. So the question here then, we have to be selective. If we want to do fine-tuning of the model, we need to know which historical data to use. The method is pretty simple. So the difference here right now, we introduce a question, we have an answer, and we have a check-in record like this. Now, we just use query similarity computation done with pre-trained Llama. So we did not do anything fancy. We basically, for each trajectory, we have we form two prompts using the trajectory template. Okay, the template that you saw before. The key prompt act like the current trajectory that it needs to be predicted, and the query prompt is the historical data. So, and then for each of the pair of key query, we feed them to pre-trained Llama, and then we compute the cosine similarity. Okay. So basically, when we form the prompt, then we only use the historical trajectory that has the highest similarity. So we end up having a shorter historical trajectory. So what we have then, we have a training data set with question and answer. And then we do fine-tuning with Flora. So what we did here, we used these three popular check-in data sets: Foursquare, NYC, Tokyo, and Goala. You might notice here that there are a lot more users in Tokyo than NYC. More POI in Tokyo. Four times the number of check-ins in Tokyo than NYC. Okay. Surprise, surprise, the result. LLM for POI. One thing I need to mention as well. We also can add history of other users who are highly similar. Again, using the cosine similarity computation and key query prompt, we can do that. So we can also include that in the prompt. So in the version where we include other users, simply because there are some model like GetNext and STHGCN that include other users. So if we only use this, it's not a fair comparison. So we use other user data as well. The performance jump is huge. And what was interesting as well, a cold start. If we use a very active user, the gain is very little. The reason is because in STSGCN, we use all history. We did not do any pruning. Remember, we pruned R1. We have to prune R1. We cannot use them all. But with inactive user, very sparse low check-in, and normal ones, our model, LLM for POI, works a lot better than graph-based transformers, state-of-the-art graph-based transform methods. That seems to work well as well for different trajectory tasks. I have another table of results I can't include here. I forgot to include, sorry. Zero-shot forecasting. Model pre-trained on Tokyo. Zero-shot forecasting on New York works better than model pre-trained on New York, tested on New York. I found that super interesting. And that
What's the solution?
As I said, potentially because of this. Tokyo has a lot more check-ins, a lot more POI, more diverse.
Have you tried the pre-trained model on New York to test on Tokyo?
Yes. Tokyo, pre-trained Tokyo, tested in Tokyo is better. But pre-trained Tokyo, tested in New York is better than pre-trained New York, tested in New York. But that time we have not done our massive POI data set, so we will soon try this again. We'll see.
But don't you need more data to infer such conclusions? I mean, it's
Absolutely. It's very hand wavy at the moment.
Yeah.
This goes back to your question, Muhammad. One time you mentioned, right? What city do we need to pre-train on? Is there a characteristic of specific city that we can do pre-training on?
Is there any specific way you sample the predictions, like top 8,
Oh, this one is only a top one. There's a more current work currently under review. We add PPO, and it's actually top K, top 20.
Is the disagreement quite high or?
Sorry, I don't remember the details.
But shouldn't be the two test sets the same size, right? Because one of the test sets is 1,000 and the other 7,000 samples, right? The two test sets.
We just follow exactly the same train test split like other papers. We didn't invent the wheel. There's already a lot of work in this area. People just keep building on each other and use exactly the same taste and trace train test validation split.
One last question. Do you have any insights for, so a bunch of papers came up which said that LLMs can't really do math. Do you know any reason why this seems to work? It's not math.
Perhaps this is not math. It's basically in here. It's so LLM, in my experience, doing fine tuning like this, is able to look at the numerical pattern and is able to do the sequence to sequence prediction well, because the backbone with the backbone transformers is already designed to be able to do that. So LLM for forecasting works well, but LLM for classification, no.
I mean, LLMs can't really reason between if 19.07 is greater or lesser than 19.7, or like similar-ish problems. 19.1, let's say 1.16 versus 1.7. So it interprets 7 as like not 70 but just 7, and then tries to think about
Why?
Sorry.
I guess.
You can learn the relationship between those two numbers.
So I guess it's a matter of where it was trained on, right? I was talking also to mathematicians. If one day, you know, LLMs would go through all the mathematic books, probably they would do mathematics, you know, equations much better than they do today, right? It's just.
Is it the problem with tokenizing? Because I mean, if you're doing byte-pair tokenizing, then it's like looking at individual numbers. So with our current system, it's looking at chunks, multiple numbers, and then it doesn't know where else.
This is a very good question because it is very much an open observation right now. How do you tokenize numerical data? And do we know, do we even need to tokenize? Do we need to move away from, to be honest, my group is actively looking at alternatives to transformers because, as I said, it's very heavy. So what is interesting with this pre-trained LLM, that the big ones, right? That I mean, this one here, for example, is used on Llama 2, but then we have these. Let me just show you. Go back to the massive POI data set if I can find it. Sorry, I can't find it. But in massive POI, we even have results using Gemini 2 and Gemini 2.5 and ChatGPT. The performance gap is getting closer, but I will say if you can't fine tune, you know there are some borrowed information that's already there in the knowledge base that is being able to know, okay, looks like I've seen that data. I mean, these are public data sets. Then potentially they've seen the data before and also already being able to learn this relationship. Okay, but if you can fine tune the model weights, then at these days, smaller model that are fine tuned still better than.
Oh,
yeah. Yeah. So, but one thing I need to say is LLM. If the dream is something like this, but for time series, we're not there yet. Okay. Train on all kind of data. This is text, images, speech, whatever. But do it on energy, human sensor, health data, electricity, trajectory, and then do a lot of the different tasks. So I think we need to think about how do we model time series alongside with the context and the observation, and that is the important part because it's very domain and context dependent for the different tasks. So, for example, one of the tasks that is harder, I'm just giving you, this is, I will say even a much smaller toy example, is time series classification. So right now, there is no GPT that can do this for you. Here's the sensor data. Can you analyze it? Or can you summarize the sensor data, right? So our work here is the first. but there's a couple steps to do it. So this was based on llama. So analyzing channels and what is the activity of the sensor. Okay, it's called sensor LLM. So one of the hardest part in here, there are two stages. For classification, it needs to be able to understand and to align the sensor and the text. And the thing is, we describe something with 1 or 2 words. In time series, it's already like. But is there a better way of describing time series? This is an open word. Is there a vocabulary for describing time series? And second, alignment for the task. Okay, because you want to do different tasks. You want to do classification. You want to do time series generation. You want to be able to do summarization. So this is a 2-stage framework that we propose. The details are in the paper. I won't have time to take a look. To show you. So there's already there's already a lot of work in LLM, but what about LLM for time series and spatial temporal data? We actually have a tutorial in this year KDD, Foundation Models for Spatial Temporal Data Science. Take a look at the survey. So conventionally, right, you have these different data sets, feature engineering, or you can do, neural network that we discussed before with transformer plus graph and all that. And you have different tasks for one model for one task, but can we do it multiple? So in this survey, we have 2 questions. How do we apply spatial temporal foundation model for each of the stage here in spatial temporal data mining? Or how do we obtain spatial temporal foundation model based on the data? Okay. The survey cover, so this is led by Yushuan Liang. I was honored to be involved in this one. There's a lot of different problem here that spatial temporal foundation model have been looking at. One of the things my contribution is the inferential problem, in fact. So there's different problem here that and different tasks, forecasting, imputation anomaly, but there's a lot of other ones that are not yet covered, like for physical grounding, for scenario simulation, for decision making, analysis of events. The questions that you want to ask, for example, what happened, where is it, what if, what to do. And I will just give you an example. So one of the prerequisites foundation model for time series is training a model on cross-domain time series all at once. Okay, so domain specific learning, you have model for each domain. Foundation model, you have all these different data sets from different domain, unified, and then it's able to do prediction on those domains. Now, where should we go? Again, LLM and foundation model are quite different. Whether you want to just fine-tune existing foundation LLM for your task, or you want to pre-train from scratch. There are 2 different capability. From my experience right now, I believe foundation model for time series is still very important because LLM doesn't handle numerical data that well yet. And there will be space for newer architecture, not transformers potentially. So in my group, for example, we're actively looking at things like Mamba. We're looking at Neural ODE, Neural SDE way of training, because then that means we do not lose the continuity of time series. or even if it's a trajectory data, the continuity is important. Otherwise, we have to break them into chunks all the time. Anyway.
So just a question: is there a space for combining these two? Let's say transforming, spatial temporal data or spatial data into text collections that can be at massive scale. Let's say maybe through map matching.
Yeah, there's a lot of work like that. For example, like there was one called Urban Clip, map data plus text, and then you
build more text.
You do clip-wise embedding, 2 different modality, and then you can then query in natural language. You can actually add the language encoder to query. There are different ways of doing this. I haven't even discussed RAG yet. You can add capability of the LLM with RAG, if you like. So you can have a RAG that is quite specific to spatial temporal data or time series data for the reasoning part. And then you can get the LLM just for the query understanding part, for example, and the conversational part. There are different ways to explore this. Absolutely. But if we want to have a truly foundation model, I think we need to have something like quite specific, like maybe like more like mixture of experts architecture rather than the dense transformer for the whole thing, because dense transformer is very heavy.
But it can be a mixture of expert with many smaller transformers.
Could be, yeah, could be. So finally, in our work, we've been doing also agentic LLM. So we have this big project called Gen AI Sim, Gen AI Simulation, agentic framework for simulation of urban behaviors. So
She had a tutorial yesterday on agentic.
yes, that's great. So with this one, I think I saw her emails. I mean, no, sorry, her instruction. There's Olama LangChain. So you can take a look if you want to do synthetic trajectory simulation, synthetic data, or synthetic behavior. We have come up with a new simulation generation engine. So it generates simulation codes. I don't have time now. It's finished my time. But next time, if you invite me again, I'll talk about agentic for urban.
Okay.
That's a separate topic. Okay. So conclusion, a lot of big challenges. There are different approaches we have proposed. All our codes are publicly available. I'm happy to collaborate. All my students are happy to collaborate, not me. So thank you.
Thank you. Do we have any questions? No? So, okay, definitely you can also talk over lunch. You will be around, I guess.
Yep.
And also for collaboration opportunities. As we said, we try to cover different thematic topics. Yeah, we also have the graph topics, spatial temporal topics. In the afternoon, it will be a network science perspective, tapping into the neural nets from a network science perspective. And this is all very interesting. Thank you very much.
Thank you.
We move on to the lunch right now.